Hello and welcome to all students. In this lecture, we learn about congruence relation on Z and we study three important theorems in congruence relation on Z. So, outline of our lecture is first we see the Fermat's little theorem and examples on Fermat-Little theorem. Then we see Euler's theorem and example on Euler's theorem. Then we see Wilson's theorem and examples on Wilson's theorem. So these three theorems are very much important in number theory and in case of congruence relation. So let us see first theorem, Fermat's theorem. So Fermat is a mathematician and he has developed this theorem. That's why this theorem is known as Fermat's theorem. So statement of theorem is, if p is a prime number, then any integer a, if p is a prime number, then for any integer a, the number a raised to p minus a is an integer multiple of p. Okay, once again, if p is a prime number, then for any integer a, the number a raised to p minus a is an integer multiple of p. Means a raised to p minus a is divisible by p, or we can say that a raised to p minus 1 is congruent, a raised to p is congruent to a mod p. So these things are one and the same. So once again, a raised to p is congruent to a mod p. Okay, in the notation of modular arithmetic, this is expressed as a raised to p is congruent to a mod p. So this is our Fermat's theorem. So let us take one example with examples of integers which satisfy this Fermat theorem. So for example, if a is equal to 2 and p is equal to 7, then 2 raised to 7 is, so we need a raised to p here, so we write 2 raised to 7. A is 2, p is 7, so 2 raised to 7 is 128, and 128 minus 2 is 126. So this 126 is nothing but 7 times 18, and this 7 times 18 means number is divisible by 7. Okay, so 128 minus 2 is divisible by 7. So 2 raised to 7 is congruent to, we can write 2 raised to 7 is congruent to 2 mod 7, or 128 is congruent to 2 mod 7, and then we write 2 raised to 7 is congruent to 2 mod 7. Okay, so this is our last step. So this shows that a raised to p is congruent to a mod p. Okay, now we write Fermat's theorem and its corollary. So we have a corollary for Fermat's theorem. For a positive prime p, for a positive prime p, if p does not divide a for an integer a, then a raised to p minus 1 is congruent to 1 mod p. So once again, for a positive prime p, if p does not divide a for an integer a, then a raised to p minus 1 is congruent to 1 mod p. So let us take one example which satisfies Fermat's theorem. For example, let us take A is equal to 4 and P is equal to 3. P is a prime and P is equal to 3 does not divides A is 4. So 3 does not divides 4, that is P does not divides A. So this is the condition for Fermat's theorem, and then we calculate what is A raised to the power P minus 1, means it is equal to 4 raised to the power 3 minus 1, and it is equal to 4 raised to 2, and 4 raised to 2 is 16. But 16 is congruent to 1 mod 3. That thing is known to you, because when we divide by 3 to 16, the remainder left is 1. Therefore 16 is congruent to 1 mod 3. Okay, so this implies that we can write A raised to the power P minus 1. 16 means A raised to the power P minus 1, and it is congruent to 1 mod 3 means P. So A raised to the power P minus 1 is congruent to 1 mod P. So this theorem is satisfied by A is equal to 4 and P is equal to 3. So you can write many examples of integers which satisfies Fermat's theorem and its corollary. Okay, so now next theorem is Euler's theorem, and the statement of Euler's theorem is: for a positive integer n and an integer a, for a positive integer n and an integer a, if GCD of a and n is 1, if GCD of a and n is equal to 1, then a raised to the power phi of n is equal to then a raised to the power phi of n is congruent to 1 mod n. So Fermat theorem says that if we have a positive integer n and any integer a such that GCD of a and n is 1, then a raised to the power phi of n is always congruent to 1 mod n. Okay, so let us take one example which satisfies this Euler's theorem. For example, if a is equal to 2, if a is equal to 2 and n is equal to 9, okay, a is equal to 2 and n is equal to 9 are the two integers such that GCD of a and n is equal to 1 and phi of n is equal to phi of 9 is equal to 6. Here GCD of a and n is 1 and phi of n is equal to phi of 9 is equal to 6. So phi of n means phi of 9 is equal to 6. Now we consider phi of a raised to the power phi of n is equal to 2 raised to the power 6, and 2 raised to the power 6 is 64. But 64 is congruent to 1 mod 9. Okay, because when we divide 64 by 9, then the remainder left is 1. Therefore 64 is congruent to 1 mod 9. So this implies a raised to the power phi of n is congruent to, so this implies a raised to the power phi of n is congruent to 1 mod n. So for integer a is equal to 2 and n is equal to 9, the Euler's theorem is satisfied. Okay, so we can write many pairs of integers for a and n which satisfies the Euler's theorem. Now let us write next theorem. Name of the theorem is Wilson's theorem. This is also important. Now the statement of the theorem is, for a positive prime p, for a positive prime p minus 1 factorial is congruent to minus 1 mod p. So for a positive prime p is any positive prime, then p minus 1 factorial, this quantity is always congruent to minus 1 mod p. So let us take one example. Suppose we have a positive prime p is equal to 5. Then p minus 1 factorial is 5 minus 1 factorial and is equal to 4 factorial, and 4 factorial is nothing but 24. But we know that 24 is congruent to 4 mod 5. But we have 4 is congruent to minus 1 mod 5. Therefore, by transitivity, 24 is congruent to minus 1 mod 5. This implies 24 is congruent to minus 1 mod 5. So finally, 24 is nothing but p minus 1 factorial, and it is congruent to minus 1 mod 5 is p. So finally we have p minus 1 factorial is congruent to minus 1 mod p. So thus positive prime p is equal to 5 satisfies Wilson's theorem. So not only 5 but all positive primes satisfies this Wilson's theorem. We can write this Wilson's theorem for all positive primes. Let us take one homework. Question number 1. Write one example for each of the following theorem. Okay, first is Fermat's theorem. Write example for Euler's theorem and write one example for Wilson's theorem. So if we have any query, about these theorems or about this lecture, you can contact